वर लगा बेटा, साउंड देते आग पडायची.
Yes, my slide is visible to everyone.
No sir.
No, now
Yes, sir. Yes.
it is also changing. Correct.
Yes. It's visible, sir.
Okay, good. Okay, so once again, good evening to everyone. So today we have a of the third class of analysis of electrical machines. So we started the first unit, so that is a basic principles for the electric machines analysis. So in the previous class, we discussed the fundamentals of electrical machines, correct? After that, we discussed the static electric machines, so that is a transformer, and then we discussed the rotating electric machines, so that is your motor as well as the generators. So we can say AC motors as well as the DC motors. Then we studied that is a MMF, magnetomotive force, electromotive force, flux, reluctance, and torque of the machine. So we can say fundamental terminology of the electric machines. Then we discussed the leakage flux and magnetic fingerings because we have to analysis the electrical machines. So this leakage flux and fingering effect both are the losses of the electric machines. So we can say we have to consider this type of losses while analysis of the electric machines. And then we discuss the operating principle of the DC machines. So I started with the operating principle of the DC machines because first time it is introduced the DC machines in the world. So that's why it is a fundamental of the electric machines. So that is a DC machines. And then we studied there is a Fleming left hand rule and a right hand rule. Yes, any confusion, any query from the previous class? Yes, any student, any query, any confusion from the previous class? Okay. Okay. So if you don't have any query, any confusion from the previous class, then we can start the new topic. So there is a fundamental terms of the electric machines, and then introduction of the induction and synchronous machine, and then starting with the simple modeling of the machines. So you can see slowly we are going to move ahead with the modeling of the electric machines. So that is we can say it is a mathematical modeling of the electric machine, so we can easily analysis the any kind of machines. Okay, so this is the today's lecture outcome. So starting with the fundamental of the uh, basic terminology of the electric machines, then introduction of the induction machines and synchronous machines, and finally we can say simple modeling of the electric machines. Yes. So starting with the rotational motion. So what is a rotational motion? Yes, this is a very fundamental concept. So maybe some student know about this thing. Those who recently pass out the BTech, but those who already pass out the BTech, maybe the before the 10 years, yeah, before the 5 years. So this is for the revision for those students. Rotational motion. Almost all electric machines rotate about an axis called the shaft of the machine. So how we can
Sir,
define?
someone is trying to join.
Just one minute. Just
Someone
please.
is requesting, sir. I think he's Robin. Is Robin Suvidi and Suruz.
Okay then. Yeah. So how we can define the shaft? So shaft is nothing but all the electric machines rotate about the in axis then we can say it is a shaft. So shaft is nothing but rotating part, and we can say it is a rotor. Correct? So rotor is rotate around the axis, then we can say it is a shaft. Because of the rotational nature of the machinery, it is important to have a basic understanding about the rotational motion. Correct? Because subject name is the analysis of the electric machines. Correct? So we have to analysis the rotation. Correct? So how we can able to rotate the machines? So what is the logic behind that? Correct? So we will discuss the brief review of the concept of the distance, velocity, acceleration, Newton's law, and power as they apply to the rotating machines. So you can see first term, that is a distance, second term velocity, third term acceleration, fourth term, that is a Newton law, fifth term, that is a power. Correct? So this term we have to analysis. Yes, I know this is the basic fundamental terminology. Maybe you studied in the 12th standard, maybe in the BTech level, but because yes, student is not same category, correct? Maybe the some is recently pass out, someone maybe the pass out before the 5 years, correct? And maybe the some student pass out the BTech in the 2011, correct? So that's why I am covering this fundamental terminology, and this is the most important terminology to understand the electric machines. So starting with the angular position, so that is a theta, correct? So we can say motor is rotating, correct? So that is a 360-degree. So we can say that is a 360-degree rotation, correct? So what is the angular position? So angular position, there is a theta, we can indicate by theta. An object is the angle at which it is oriented. Measure from some arbitrary reference point. So we can say, suppose this is your stator part and this is your rotor part, and this is our reference axis. So we can say this is the stator and this part is the rotor, and this one is our reference axis. So we can say, suppose motor is rotating at omega speed, so we can say yes, angular position, otherwise the angular position we can say theta, it is rotating anti-clockwise direction, correct? So we can say angular position of an object is the angle at which it is oriented and measure from the arbitrary reference point. So we can say this is your reference point and it is rotating something like that, maybe the clockwise direction, maybe the anti-clockwise direction. Angular position is usually measured in the radians, otherwise the degree. Yes, student, unit is the most important, correct? As we are the engineers, so we have to define each and every quantity with the unit. So whenever we can write the theta, then we can say unit is a radians, otherwise the degree. It's corresponding to the linear concept of the distance along the line. So we can say yes, that is a rotation, maybe the linear rotation, maybe the circular rotation, correct? So that is a depend on the which type of rotation, correct? So we can say the linear motor, different type of motor is available. So that is a depend on the type of application we can use the machine, correct? Maybe the motor, maybe the generator. So ultimately there is a position, angular position theta. So theta is nothing but just rotation, correct? Then angular velocity. Angular velocity is nothing but your speed, correct? We can say speed, and it is indicated by the omega. Angular velocity, otherwise the speed, is the rate of change in the angular position. Yes, so we can say theta is changing with respect to time. So we can say d theta by dt is equal to omega, correct? So theta is changing with respect to time. Then
Excuse
we
me,
can
sir.
say, yeah.
Sir wants to join. I think.
What? Somebody want to join?
Yes, yes, sir. Sir wants to join.
Yes, now I think we have a full strength. Total number is 20. Yeah. Yes. So we can say angular velocity is nothing but your motor speed, correct? So we can say how we can define the motor speed. So we can say rate of the change of the angular position. your theta is changing with respect to time. So you can say d theta by dt, correct? D theta by dt. So theta is changing with respect to time. That is nothing but your speed, correct? It is assumed positive if the rotational is a counterclockwise direction. Yes, we can define speed is maybe the positive, maybe the negative, correct? Maybe the forward direction, maybe the reverse direction. Suppose you are coming the reverse direction, we can say it is your negative speed, correct? Suppose you are going the forward direction, then we can say the positive speed. So we can define it is a clockwise direction, otherwise the anti-clockwise direction, otherwise the counterclockwise direction, correct? Angular velocity is the rotational analog of the concept of the velocity on the line. Yes, we can say the linear motion, otherwise the non-linear motion, correct? So we can say it is a depend on the speed. So we can define by V. One-dimensional linear velocity along the line is defined as the rate of change of displacement
कहाँ?
along the line R. Student, please mute your microphone, correct? Otherwise, you are disturbing the class. So it is my humble request, please mute your microphone. Yes, the rate of change of displacement along the line, there is a R with respect to time. So we can say V is equal to dr by dt. So this equation, it is in the case of the rotational, and this equation in the case of the linear motion. So we can say V equal to dr by dt, and R is nothing but your line, correct? Similar to angular velocity, there is a omega. So this is your omega is the defined as the rate of change of the angular displacement. So we can say omega equal to d theta by dt. That is equation number 2. So all equations are most important. So just remember this type of fundamental equation, correct? I hope you already know, but this is just revision, correct? If you forgot, then please revise this concept. Then angular acceleration, then we can say it is a, okay, angular acceleration. Angular acceleration is the rate of change in angular velocity with respect to time. So we can say dv by dt, a equal to dv by dt. It is an angular acceleration. So indication symbol, otherwise we can say the notation of the acceleration, there is a small a. It is assumed the positive if angular velocity is increasing in the algebraic sense. Yes, we can say acceleration is positive, your speed is increasing, correct? Otherwise, velocity is increasing because acceleration is directly proportional to velocity. Yes, velocity is increased, then we can say it is positive. Velocity is decreased, then we can say it is a negative. Just as a one-dimensional linear acceleration is defined by equation, there is a equal to dv by dt, where a is a acceleration and that is a unit is a meter per second square. Angular acceleration is defined by a equal to d omega by dt. So this is your angular acceleration, correct? So that is a equal to d omega by dt. Yes, now torque. Whenever we can say electric machines, then we have to analysis the torque and the speed. How we can take the torque and speed, that is a depend on your angular moment of angular rotational, linear rotational. That's why I discussed this term, angular velocity, angular position, acceleration, correct? And then we can say torque. So how we can define the torque? So torque is nothing but your force into acceleration, correct? So we can say this is the any shaft, correct? So this is your shaft, correct? And this is your rotor. We can say this is your rotor, correct? So we can say this force, we can apply the force, correct? So we can say torque is not generated. So torque is a 0. So you can see this is the same alignment, correct? So this is alignment is the same. So we can say torque is not generated, correct? So we can say torque is a 0. So torque is a 0 Newton into meter, correct? Because alignment is the same alignment. Suppose force alignment is a different to the rotor, then we can say yes, torque is generated. But how much torque will generate, that is a depend on the force value. How much force you are applying into the motor, correct? So we can say in the second case, torque is generated, but some value, and how much value, that depend on the your force. So you can see fundamental concept. We have to apply the force to the machine, and then torque will generate. And how much torque will generate, that depend on the input of the motor, and that is a force. Correct? So you can see figure 1a, a force applied to the cylinder so that it is passed to the axis of the rotational. So we can say the torque is equal to 0. But in the second case, a force is applied to cylinder so that line of the action misses the axis of the rotational. So we can say torque is a counter clockwise direction. Yes, we can say it is a clockwise and anti-clockwise, depend on the force. Maybe the force is positive, maybe the force is negative. So depend on this force, we can say torque is generated, that is a positive direction, otherwise the negative direction. So is a straightforward definition, otherwise we can say the single statement definition. A linear motion, a force applied to the object cause it is a velocity to change. Yes, we can apply the force, so it will change the velocity. That is a simple thing. In the absence of the net force on the object, its velocity is a constant. Yes, suppose we cannot apply the force, then whatever velocity, maybe the 1 meter per second square, maybe the 0 meter per second square, whatever velocity, it is a constant because there is no external force. So you are not given the any external force. So whatever position is that, so there is a same position. Correct? Okay. A greater force applied to the object, the more rapidly of the velocity change. Yes, we can say suppose you are applying the more force, so you will get the more velocity change. Yes. When the object is rotating, an angular velocity is a constant unless a torque is present on it. When the object is rotating, correct? Suppose motor is rotating, angular velocity is constant unless the torque is present on it. Correct? That greater the torque on the object, more rapidly the angular velocity of the object change. So simple, you can remember torque is directly proportional to the velocity. Otherwise, you can say force is directly proportional to the velocity. Okay. Yes. So what is a torque? Torque, we can say it can be the loosely be called the twisting force on the object. So we can say twisting force of the on the object, it is called the torque. Okay, suppose somebody asking what is a torque. The torque is nothing but twisting force on the object. That is your simple we can say it is a torque. Correct? Imagine a cylindrical cylinder that is free to rotate about its axis. So you can see simple cylindrical, correct? Simple, you can assume the simple cylinder. So it is free to rotate around its axis, correct? If the force is applied to the cylinder in such a way that is a line of the action passes to the axis, so you can see figure 1, the cylindrical will not rotate. Yes, so this figure 1, correct? So you can passes the force that is the same axis, so it is not able to rotate, correct? So we can say torque is a 0. We can say it is a locking condition, correct? Yes, it is not rotated. Yes, the torque is object is defined as the product of the force. How we can define the torque? So we can say torque is a twisting force, correct? But how we can define the torque in the terms of the mathematical equation? Force applied to the object and smallest distance between the line of the action of the force and the object axis of the rotational. So torque is defined by the two terminology. There is a force, okay. One is a force and second is a perpendicular distance. Okay, how much travel. So you are supposed to apply the 1 Newton meter force, correct? And maybe it is travel is maybe the 1 meter, correct? So we can say torque is your force into the R into sine theta. Why sine theta? Because of angular movement, correct? We are discussing the motor, so that is an angular movement. That's why it's a sine theta. And F, that is a force. You are applying R, that is your distance, but the perpendicular distance, and sine theta, that is your angular movement. So we can say finally torque is equal to R into F into sine theta. Okay. Yes. Any question till now? Yes, any question till now? Okay, good. So where theta is the angle between the vector r and the vector f. Yes, so that is a vector r. So suppose maybe this is the r and this is the f. So this angle is a theta, and theta is rotating, maybe the clockwise direction, yeah, maybe the anti-clockwise direction. Okay, so this is simple. Okay. Yes, you can see. So this is your any cylinder, correct? And this is your axis, correct? So you can see it is rotating in the theta direction, correct? So there is a 180-degree minus theta, and theta maybe there is a maybe the 30-degree, maybe the 40-degree, maybe the maybe the 180-degree, correct? So we can say here is a theta and theta is rotating, so we can say r sine theta, r sine 180-degree minus theta, correct? So we can say is equal to r sine theta. Okay, so this is simple relation and there is a mathematical term, correct? So sine theta cosine theta. So we can say torque is equal to perpendicular distance into force. So yes, we can say torque is nothing but F into R sine theta, and R is a distance. So you can see this is the R. R is a distance. How much distance? That is a perpendicular distance, and we have to apply the force. So we can say torque equal to F into R sine theta, correct? And this term, that is a most important term. So how we can define the torque? Okay, so torque is equal to R into, sorry, force into R into sine theta. Okay, so this is the terminology for the torque. Yes, now Newton laws. Now Newton law of the rotation. Newton law object moving along the straight line describe the relationship between the force applied to the object and it is a result in the acceleration. Yes, simple F into F equal to ma. Yes, this is a simple concept. We can define the Newton law. There is a force equal to mass into acceleration. There is a F equal to m into a. So we can say F equal to net force applied to the object in the Newton. Correct. Unit is a Newton. M, that is a mass of the object, that is a kilogram, and A, that is a resulting acceleration in the radian per second square, correct? Otherwise the meter per second square, correct? So this is a simple Newton's law of the rotational. Otherwise, in the terms of the torque, correct? In the terms of the torque, how we can define the newtons? This relation is called the Newton's law of the rotational, correct? So we can say torque is equal to J into A. And what is a J? J is nothing but moment of inertia. J is nothing but moment of inertia. Unit is a kilogram into meter square. Okay. So this is the not K. So this is the kilogram into meter square. Okay, not kilometer square. Correct. So this is the kilogram into meter square. There is a moment of inertia. And A, there is a acceleration radian per second square. And torque, there is a applied torque, that is a Newton into meter square. Yes, the unit of moment of inertia, that is a not kilometer square, that is a kilogram into meter square. Yes, then work. Okay, so what is the work? For the linear motion, work is defined as the application of the force to the distance. Yes, we can define the work. So that is simple definition. Work is equal to integration of force into distance. Correct? Okay, so work, there is a force through the distance. So we can say integration of the force into distance. So that is a work done. So unit of work, there is a joule in the SI unit. If force is constant, suppose your force is constant, so a constant term of force, we can say W equal to F into R. Correct? So if your force is constant, so we can say W equal to force into R. So no need to do the derivation, correct? Sorry, integration part, correct? Suppose force is constant, so we can say yes, we have a 5 Newton meter into the distance, correct? So no need to do the integration of the to derive the work. What about in the terms of the torque? So we can say work is equal to integration of torque into d theta. So suppose torque is constant, so we can say W equal to torque into theta. That is equation number 10. Okay. Yes, last term, that is a power. Okay. So finally we have to analysis the power. Okay. So we can say voltage. Voltage is directly proportional to the speed. Current. Current is directly proportional to the torque, and then power. So power is nothing but product of the voltage and current. So there is a electrical relation. What about the mechanical relation? So power is nothing but product of the torque and the speed. Correct? So equation of the power, power is nothing but P equal to dW by dt, and dW is nothing but your work. Correct? So usually measure power in the joule per second. Correct? So that is a unit of the power, that is a joule per second. Correct? Work, that is a joule, and time, that is a second. So we can say joules per second, otherwise the watt. So in the terms of the force, we can say P equal to dW by dt, and W, that is a nothing but F into R. Correct? So we can say F is a constant. So we can say F dr by dt. So we can say dr by dt is nothing but your V. So we can finally write P equal to F into V. Correct? So this is the power for the linear motion. F into V, and V, that is a velocity for the linear motion. What about in the rotational motion? Correct? So power in the rotational. So we can say P equal to dW by dt, and W is nothing but torque into theta. Correct? So theta is continue rotating. So we can say torque is a constant. So we can say d theta by dt, and d theta by dt is nothing but your omega. Correct? So we can say power in the terms of the speed into torque, we can say power is equal to torque into omega. So we can say mechanical power is equal to torque into speed. What about the electrical power? Power electrical is equal to V into I. Correct? So this is the electrical power. So you can see voltage is directly proportional to the speed, and current is directly proportional to the torque. So we can say power is nothing but torque into. So this relation, equation number 1 to 13, are very important in the study of the electrical machines, because it can be described the mathematical power on the shaft of the motor or generator. Yes, that's why student I cover this fundamental concept of the electric machines. Otherwise, we can say fundamental terminology of the electric machines. So this is a simple term starting with the velocity, acceleration, linear motion, angular motion, speed, work, and finally power. Okay. Yes. Any confusion? Any doubts till now? Yes, student. I hope no confusion, no doubts. Then move ahead with the magnetic field. Now slowly we are going to the magnetic field, correct? And then we can able to understand how we can rotate the motor. So magnetic field, what is a magnetic field? In the yesterday class, I already discussed this magnetic field, not the yesterday class, in the last class, correct? Magnetic field are the fundamental mechanism by which energy is converted from one form to another form, maybe in the motor, generator, and transformer. Yes, we discussed in the last class, whenever we can say machine, then we can say the rotating machines as well as the static machine. Static machine is nothing but your transformer, correct? So transformer is a static machine, correct? And rotating machine we can say motor and generator. Four basic principles describe how magnetic field are used in this device. Which device? So there is a motor, generator, and transformer, correct? So first basic principle: a current carrying conductor, a current carrying wire produce the magnetic field in the area around it. Yes. So in the DC machines, in the last class we discussed what is the principle of the DC machine. Whenever current carry conductor put in the magnetic field, it will create the force. Correct? So that is the first rule. Second, a time changing magnetic field induce the voltage in the coil. Yes, so there is a Faraday laws. We can say induced EMF, that is opposed we can say minus n d phi by dt, correct? So we can say time changing magnetic field induce the voltage in the coil of wire if the passes through that coil. This is the basic of the transformer action, correct? Induce EMF minus n d phi by dt. Third rule, the current carrying wire in the presence of the magnetic field is the force induced in it. This is the basic for the motor action. When the current carrying wire in the presence of the magnetic field, correct? So here is induced because that is your transformer. Here is the presence of the magnetic field is the force induced on it. Last one and fourth one, a moving wire in the presence of the magnetic field has the voltage induced in it. So that is nothing but your generator, because we want the voltage in the case of the generator, but in the case of the motor we want the force, correct? So this fourth terminology is required. So you can see a current carrying wire in the presence of the magnetic field has produced the force, but moving wire in the presence of the magnetic field is the voltage induced in. Just reverse terminology for the motor and generator, correct? So production of the magnetic field, how we can produce the magnetic field, correct? So that is the most important part, production of the magnetic field. Now we have to produce the magnetic field. Basic law governing the production of the magnetic field by the current is Ampere law. Yes, we all know the Ampere's law, correct? So basic law of the governing the production of the magnetic field by close integration of H into dl is equal to I net. So close integration H into dl is equal to I net. That is the Ampere law. What is the H, I net and dl? So where H is the magnetic field intensity, which we already studied in the last class, correct? You remember this equation B equal to mu H, correct? In the last class we discussed this equation. So in the last class I already told, so there is a H is nothing but magnetic field intensity, okay, and B is nothing but your flux density. So you can see close integration of H into dl is equal to I net. So H is a magnetic field intensity produced by the current, that is I net, and dl is the differential element length along the path of the integration. So L is a length, H is the flux density, I net, there is a current passing to the coil. So SI unit, J is a measure in the ampere and H is a measure in the ampere turns per meter. Okay. So this is the node J. So this is the current I net. I net is measured in the amperes and H is measured in ampere turns per meter. Okay. So unit of H is equal to ampere turn per meter. Meter, why meter? Because length we measure in the meter as per the SI unit. Okay. So this unit is the most important. Flux density, magnetic field intensity unit is a ampere turn upon meter. Yes. Now we can consider the simple magnetic core. Simple magnetic core. So you can see this is the magnetic core, correct? And this is the winding. Okay. So this is number of turns. So this is the flux. Okay. And this is supply current. So we can say I. To better understanding the meaning of this equation, it is helpful to apply this simple example in figure 1. Yes, so we studied till now total 15 equation, correct? 15 या 13 equation, correct? So for better understanding, we can consider the simple coil, correct? Simple magnetic core. Figure 1 show the rectangular core with the winding of n turns. Here we can say this is the n turns. Okay, so this is the n turns of the wire wrapped around the one leg of the core. So we can say this is the first leg, otherwise primary, and this is the secondary side. Correct. So we can say the primary side wrapped around the one leg of the core. If the core is composed of the iron or certain other similar the matter, collectively called the ferromagnetic. Normally we use the ferromagnetic material, correct, to design the core. So it is up to you. You can also change this material, but normally we can use the ferromagnetic material. Essentially, all the magnetic field produced by the current will remain inside the core. So the path of the integration in the Ampere's law is the mean path length of the core, that is a LC. So you can see LC is nothing but length of the core. Correct? So you can see this is the length of the core. This is your LC. Okay, L indicate that is a length and cell C indicate your core. Okay, the current passing within the path of the integration, there is a I net is then Ni. Yes, why Ni? So this Ni, I is equal to I net. Okay, whenever it's a small I, then consider there is a I net. Since coil of the wire cut the path of the integration, there is N times, while current carrying there is a I. Correct. So by the Ampere law, we can write H into LC is equal to N into I net. Correct. How much field is produced? That is a H into LC is equal to N into I net. That is equation number 2. Here H is a magnitude of the magnetic field intensity vector H. Okay. So there is a vector quantity. That is a, we can say magnitude as well as the direction. Therefore, magnitude of the magnetic field intensity in the core due to the applied current, there is a I is equal to H is equal to N I net divided by LC. So what is the formula for H? H equal to N I divided by L. Okay, so L is a length, L is the number of turns, and I is equal to current passing through coil. So we can say unit of L ampere turn divided by meter. So this is the unit. Okay, done. Yeah. So relationship between the magnetic field intensity H and the resulting magnetic flux density, there is a B produced within the material is given by B is equal to mu into H, where B is a magnetic field, correct? Magnetic flux density, B is equal to resulting magnetic flux density, H equal to magnetic field intensity, and mu equal to magnetic permeability of the material. So we can define mu equal to mu naught into mu r. Mu naught, that is the air permeability, air, and mu r, that is a relative permeability. That is otherwise the material permeability. Okay, relative otherwise the material permeability. Material relative permeability. Correct. So mu we can note down by mu naught into mu r. Yes, student. Till now, any confusion, any query? So till now we completed the fundamental terms, fundamental of the electric machines. Now we are move ahead with the modeling part. How we can modeling the electric machines. Okay, no confusion. Then we will go ahead with the modeling part. Starting with the DC machines. Simple, draw the equivalent circuit of the DC machine. So how we can draw the equivalent circuit of the DC machine? So there is a simple supply voltage armature voltage, so this is your switch, correct? So this is your switch. Armature resistor and back EMF, correct? So this is the back EMF, so we can say KE into omega. Okay, and this is simple switch. Okay, so this is a simple equivalent circuit of the DC machines. So we can say current is flowing I. So we can say equivalent circuit of DC machines. Correct? Now we have to analyze this circuit. So starting with a simple analysis, just apply the KVL. So we can say now we have a single loop, only one loop, apply the KVL. So KVL is saying voltage in the circuit is equal to 0. Okay, voltage drop is equal to 0. Okay, so we can write KVL equation for this circuit. VA is equal to IA RA. So this is your IA armature current. We can say the armature current. IA RA plus your back EMF. Correct? So this is nothing but your back EMF, EB. Correct? So EB is nothing but your back EMF. Electromotive force. And K is nothing but back EMF constant, and omega is nothing but your speed. Okay, so you can see simple voltage equation for this circuit. VA is equal to IARA plus EB. So we can say equation number 1, correct? And EB is nothing but your K into omega, equation number 2. And what about torque? Electromotive torque, that is nothing but your power, correct? So we can say KT into IA, equation number 3, correct? So we can say torque is directly proportional to the current, speed is directly proportional to the voltage. Whenever you remove the proportionality, then we can say there is a constant, correct? So this KT is a torque constant. Yes, student. Any confusion, any query? So this is a simple KVL equation. We are applying the KVL. There is a Kirchhoff voltage rule. Otherwise, Kirchhoff voltage law in the equivalent circuit of the DC machines. Okay. So this equation for the steady state analysis. Okay. So this equation for the steady state analysis. So what is a steady state and dynamic? Yes, any one student? Steady state and dynamic analysis. Any idea? Any one student? What is the meaning of steady state and what is the meaning of dynamic? Any idea? Any one student?
So steady state, in a steady state, all the parameters values are constant. In dynamic state, the values rapidly change within short duration of time.
Okay, very good. What about the other student? Any other student? Yes, any more student want to add the anything? Okay, so steady state means, so there is a constant value, parameter is constant, there is a not change with respect to time, correct? Then we can say the steady state. And dynamic parameter is change with respect to time. So we can understand by the graph. So maybe this is a time and this is the maybe the speed, correct? And this is your zero. So starting with the zero, speed is increasing. So speed is increasing slowly, 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 slowly. It is stable sometime. It will take some time and then it is stable. Okay. Otherwise, I can say yes. So suppose this is a speed response for the maybe the DC motor, correct? So we can say this reason. What is the name of this reason? Yes, any student, what is the name of this reason?
Transient and dynamics, sir.
Very good. So this one is a transient plus dynamic. Okay, so we can say this reason is transient plus dynamic and this one is a steady state, correct? So in the simple language we can say transient means it is a response will change with respect to time, correct? But in the case of the steady state, your response is not getting changed with respect to time, it is a constant. Okay, so this is simple. So we have to analysis the electric machines in the both conditions, steady state condition as well as the dynamic condition. Okay, so this is a simple equation for the DC machines, correct? Now we can see what is a simple equation for the induction motor. Three phase induction machines. How we can run the induction machine, what is the working principle, I am not going to cover this thing because this is a fundamental concept. If you forget this thing, then please revise your concept. Okay, maybe you can get the help from the YouTube. Okay, otherwise maybe I already said the books, then you can just refer that books, correct? So please revise your concept if you forget the fundamental concept of the machines, correct? I try to cover the basic concept, but for each and every component, I am not going to cover. Correct? Otherwise, I cannot able to complete the syllabus. So three-phase motor, correct? So three-phase motor is nothing but we can say three-phase supply, correct? Correct. So we can say this is a three-phase motor, correct? So we have to supply the three-phase winding, correct? So we can say R phase, Y phase, and B phase. So we have to supply the three phase, and this is your, we can say the shaft. Otherwise, we can say the rotor. It is rotating, correct? So this is simple machine. So we can say this is a three-phase induction machine. Okay. So this is an induction machine. So we can say single-phase induction machine as well as the three-phase induction machine. So we can say this is the input, and here is a output. Okay. So what is the equivalent circuit for this three-phase induction machine? Correct. So we seen the equivalent circuit for the DC machine. So now what is the equivalent circuit of the induction machine? So we can say yes, supply, because AC motor, induction is AC motor, so AC supply, then resistor, then inductor. So we can say R1, L1, okay, then mutual coupling, so this is a similar to your transformer equivalent circuit. So we can say this is the R2, this is L2, and here your sleeping, correct? So we can say R2 days is nothing but 1 minus S divided by S, and S is nothing but your sleep. RM XM, correct? XM, otherwise the we can say LM. Everywhere we are writing L, so we can say LM, and this is your IM, and here is your I1, and here is your supply voltage. Okay, so you can see this is the equivalent circuit, figure 1. Equivalent circuit of per phase induction machines. Okay, so this is the simple equivalent circuit of the per phase induction machines, and this is a similar to your transformer. If you want to draw the transformer equivalent circuit, then this is the same circuit, correct? So R1 and L1, there is your we can say it is a stator resistor inductor. R2 and L2, there is your rotor, and when we draw the rotor part, then sleep is there. So S is nothing but your sleep, correct? And sleep is what? There is a difference between the synchronous speed and the actual speed. There is a sleep, correct? So we can say induction machine is never ever operate on the synchronous speed, correct? So that's why we can say in the induction machine sleep will generate, okay, but in the synchronous machine sleep will not generate. So there is a major difference, and this type of question many industry will ask for the interview, correct? So why synchronous motor is not generate the sleep, but why induction motor will generate, correct? So this is simple difference, because in the synchronous machine we are applying the two power supply, rotor as well as stator. So it is not generate the sleep. Both are rotating the same speed. Stator as well as the stator magnetic flux and the rotor magnetic flux. Both are rotating the same speed, so that's why it is not generated. But in the case of the induction machine, we are supplying only to the stator. We are not apply the supply voltage to the rotor part. So that is a stator magnetic flux line and rotor magnetic flux line, both are the not equally rotational. So that's why sleep will generate, correct? So magnetic, your stator magnetic flux is ahead compared to the your rotor magnetic field. Okay, so we can say sleep is nothing but sleep is equal to omega s, that is a synchronous speed, minus rotor speed divided by synchronous speed, correct? So that is your sleep is equal to omega s minus omega r upon omega s, and where omega r, that is your actual speed. Actual speed or rotor speed. Correct? So this is the simple equivalent circuit of the your per phase, three phase equivalent circuit of the per phase induction motor. Correct? Okay. Yes. Any confusion? Any query? Yes. Yes, student. Any confusion? Any query? Yes. So now I close this class here. Okay. So key point from the today's class. So there is a fundamental terms of the electric machines and introduction of the induction motor and synchronous machine we will study in the next class. Correct? And simple modeling of the machines. So there is a DC machines as well as the induction machines. In the next class, we will study the per phase equivalent circuit of the synchronous machine, and then we will study the detailed mathematical modeling, otherwise the simple modeling equation of the coil. Correct? So we can go detail with the magnetic flux line, how much magnetic flux will produce. Correct? So slowly we are going in the detailed analysis of the electric machines. Yes, now if you have any question, any query related to today's class, then please ask me. Otherwise, we can stop class here. Yes, student. Any query, any confusion? Okay, no query. Then we can stop the today's class. Correct? And we will meet on the Monday again. Okay. Okay. Thank you so much. So you can leave it. And thank you so much to attend this class.
Okay, sir. Thank you. Thank you for teaching.